everyone and welcome to your physics tutorial. Today we're going to talk about one of the most important foundations of all scientific studies, system of measurement.
Every experiment, every calculation, and every discovery depends on one thing: accurate measurement.
Without it, there is no way to compare results, repeat experiments, or build technology that work consistently. So, let's explore how we, as scientists and physicists, measure the world accurately and systematically.
You might wonder, why do we even need a system of measurement? Imagine, if every country or even every person used their own way of measuring things. One person's foot could be 10 inches, another could be 13. Total confusion. That's exactly how it was centuries ago.
To fix this, scientists developed the International System of Units, or ESA, which stand for Système International d'Unité in French. It's the global standard for measurement used in science, technology, medicine, and even in SI systems allows everyone from engineers to doctors to students like you to measure and communicate results accurately and consistently around the world.
The SI system is built on 7 fundamentals or base units, which are the building blocks for all physical measurements.
Length is measured in meters, written as m, which tells us how long or how far something is. Mass is measured in kilograms, written as kg, which tells us how heavy an object is. Time is measured in seconds, written as s, which helps us record how long events last. Electric current is measured in amperes, written as A, which tells us the flow of electric charge. Thermodynamic temperature is measured in kelvins, written as K, which show how hot or how cold something is based on molecular motion. Amount of substance is measured in moles, written as mole, used to count particles like atoms or molecules. Luminous intensity is measured in candles, written as CD, which tells us how bright a light source is.
These 7 base units form the foundation of all scientific measurements. Most of the quantities we measure aren't just one of the 7. They are combinations of them. These are called derived units. For example, when we calculate area, we multiply length by width, giving us square meters. For volume, we multiply 3 lengths, resulting in cubic meters. For speed, we divide distance by time, giving meters per second. Even force, which we measure in newtons, is derived from the base units. It's equal to 1 and is equals to 1 kg times meter per second squared. If you know the formula, you can figure out the derived unit. That's the beauty of the SI system. Everything connects logically.
In physics, we often deal with numbers that are extremely large or incredibly small. The distance between planets can reach billions of meters, while the size of an atom is measured in nanometers. Writing all those zeros would be impractical, so we use metric prefixes, which represent powers of 10. Kilo means 1,000, milli means 1,000, mega means 1 million, giga means 1 billion, micro means 1 million, and nano means 1 billion. These prefixes makes it easier to express and convert values, whether we're studying galaxies or atoms.
Let's try an example using dimensional analysis, a method used to convert one unit to another. Suppose we want to convert 5 kilometers to meters. We know that 1 kilometer is equals to 1,000 meters. So, 5 km times 1,000 meters over 1 km is equals to 5,000. This ensures our final unit is correct. This process of cancelling and rearranging units keeps your measurements accurate and prevents calculation errors.
Now, let's try a few solving examples using the SI system. For example 1, we have here an converting volume. Convert 250 milliliters to liters. We know that 1 liters is equals to 1,000 milliliters. So, 250 milliliters multiplied by 1 liter divided by 1,000 milliliters is equals to 0.25 liters. Another example is speed calculation. If a car travels 200 meters in 10 seconds, the formula for speed is velocity is equals to distance over time. So, velocity is equals to 200 meters divided by 10 seconds is equals to 20 meters per second.
All of these values use SI units, which makes your data clear, comparable, and globally understood. Now, let's bring science to life and see how the system of measurements shapes our world through real-life applications.
In engineering, accurate SI-based measurements are essential to ensure the safety and stability of structures like bridges and buildings. Engineers calculate pressure, force, and load capacity using SI units, such as pascals and newtons. Even a tiny error could lead to major structural problems. Here is a problem. An engineer needs to find the pressure on a steel beam that supports a force of 10,000 Newton over an area of 2 meters squared. Solution. Pressure is equals to area over force. Pressure is equals to 2 meters squared over 10,000 newtons is equals to 5,000 pascals. Answer. The beam experiences 5,000 pascals of pressure. Using SI units helps engineers around the world communicate and compare measurements precisely, ensuring that all designs follow the same safety standards.
Real-life application 2. Medicine and health. In the medical field, the SI system is also crucial. Doctors measure body temperature, dosage, and blood volume using standard SI units to ensure accuracy and patient safety. A small conversion mistake in medicine could be life-threatening. That's why SI consistency is vital. Problem: a doctor prescribes 0.5 grams of a medicine, but the syringe measures in milligrams. To convert grams to milligrams, we know 1 grams is equal to 1000 milligram. So for the solution, 0.5 gram times 1000 milligram is equal to 500 milligram. The patient should receive 500 milligram of the medicine, ensuring proper dosage through correct unit conversion. This consistency keeps patients safe and ensures that treatment are effective across all hospitals and pharmacies.
The SI system is also vital in modern technology. Devices like smartphones, laptops, and computers rely on measurement at the micro and nano levels. From chip sizes to data transfer rates, scientists and engineers use prefixes like micro and nano to describe components that are extremely small. A smartphone processor is built with transistors that are 5 nanometers wide. Convert this to meters. 1 nanometer is equal to 10 raised to negative 9 meter. 5 nanometer is equal to 5 times 10 raised to negative 9 meters. Each transistor is 0.0000005 meters wide. This shows how the SI system helps scientists work with extremely small measurements, allowing innovation in computing and technology to keep advancing every year.
The system of measurement is more than just a list of units. It's the universal language of science. The 7 base units form the foundation. Derived units combine them to measure complex quantities, and metric prefixes make it easier to handle large and small values. From engineering and construction to medical safety to technology and electronics, the SI system ensures precision, reliability, and consistency worldwide. It connects physics to everyday life and helps us understand the world with accuracy and confidence. So, thank you for watching this tutorial video. I hope you learned something new and meaningful today. Study smart, stay curious, and see you in our next physics lesson.